In linear regression, we use mean squared error as a loss function. When applying gradient descent to this loss function, we assume this forms a convex shape and find a point at the bottom of this convex shape that results in the minimum error and corresponding parameters are optimal for the given data. But the data is different for each use case. The data does not necessarily follow a normal distribution. This leads us to the question, why does the minimizing squared errors work even when the original data does not follow normal distribution? Is this assumption valid for all types of data distribution? One of the key statistical reasons this approach works in practice is called the Central Limit Theorem. In this video, we will see what does a Central Limit Theorem state, a look at the random data and the distribution it follows, and how does it translate to a normal distribution. Also, a Python code with the random data of about 100,000 samples and see Central Limit Theorem making this data a bell curve. Welcome to Decoding Complexities, I am Pradeep. Central Limit Theorem states that when we extract sufficiently large samples, ideally greater than or equals 30, from the random distribution and average these samples, the resulting distribution tends to follow a normal distribution, regardless of the original distribution. When I heard about this for the first time, I thought, why would this always work? Would this not depend on the input data distribution? But as I learned this, I realized one thing. The key point here is that taking sufficiently large number of samples and averaging to produce data in the resulting set. It's not just taking the data randomly from the input and moving it to the result set. Let's take a look at an example by taking 100 random numbers between 1 and 100. The data is randomly distributed, and when plotted on a graph, it almost appears like a rectangle. Let's extract 30 random samples from this data and plot this again on the graph. There is no much difference when compared to the original distribution. Let's do this again. Extract 30 random samples, average them to produce a data point in the resulting set, and repeat this process for 30 iterations and plot this data on the graph. We can clearly see the data following normal distribution with a bell curve. We will implement this in Python. Instead of 100 samples, we will take about 100,000 samples and plot this data. As in our example, we can see that this data is forming a rectangle-like shape when plotted as an histogram. Like in our previous example, we will extract a sample 10,000 times and plot the resulting dataset as a histogram. We can see that the resulting plot is almost same as the original data. As a next iteration, we will take 2 random samples and average them for 10,000 times. When we plot this data, we can see the shape of the resulting plot changing. Instead of a rectangle, we can see it forming a triangle-like shape. This is the point where we realize the magic of the Central Limit Theorem. For the next iteration, we take about 30 random samples and average them for 10,000 times. Plotting this data will result in a bell curve. We can also try this on the data that follows an exponential distribution. The result of the Central Limit Theorem would still follow the normal distribution. Does it appear like a cheat code? Doesn't it raise a doubt on why do we really need to take an average? Why does this relate to linear regression? The answer directly takes us to the loss function used in linear regression, the mean squared error. We calculate the average of the squared errors, which is much like what we have explored in the Central Limit Theorem. Central Limit Theorem explains the statistical behavior of averaged errors, while gradient descent is simply the optimization method used to find the minimum. We now understand why a loss function mean squared error aligns well with the bell curve and makes it reliable for linear regression. But the question of how to find the perfect bell curve for our data and how we use this for training still remains. This can be achieved by using a technique called maximum likelihood estimation. It is the engine behind various machine learning models from logistic regression to neural networks. And this is what we are going to decode in the next video. If you prefer reading, a link for the detailed companion blog post and the Python notebook used is in the description. If this video helped you understand Central Limit Theorem, hit that like button and consider subscribing as we continue to decode the complexities of machine learning. Thank you for watching, and I will see you in the next one.